Hi, I'm Rick Powell from Nanoprobes, and today we're going to talk about one probe, two labels. And that's all about our combined fluorescent and gold labeled immunoprobe, FluoroNanogold, which provides you with a way to do correlative fluorescence and electron microscopy, and a way to check your immunoelectron microscopic labeling before you actually do your electron microscope specimen processing. To get started, we're going to cover today what is FluoroNanogold, why you should use it, what are its key features, advantages, and applications. And we're going to move on to some technical help, some tips and tricks to give customers who are using this probe and want to get the best optimal results. This is FluoroNanogold, and it pretty much is what we said it was earlier. It's actually a gold nanoparticle and a fluorophore separately linked to an antibody or a targeted protein. In this case, a Fab prime fragment of an antibody, which has a fluorescein and our 1.4 nanometer Nanogold gold label linked to it. Why use FluoroNanogold? As we mentioned, you can check immunolabeling by fluorescence before you actually start a lengthy or complex or difficult electron microscopic prep, so you don't have to lose time doing an EM prep when you're not sure if your labeling has worked. Check it first by fluorescence. This probe was designed for correlative light and electron microscopy, or CLEM. And it lets you correlate the light microscope level fluorescence signal with the macromolecular level electron microscope resolution signal obtained by the gold nanoparticles. And you can correlate transmission electron microscopy, scanning electron microscopy, and even X-ray fluorescence with the light microscope fluorescence, and see where your features, where your targets are located at different levels of magnification, different levels of resolution, and a different level of cellular context. Here are some of the characteristics of fluorescence versus electron microscopy. Fluorescence microscopy shows you the cell and tissue scale distribution of your target. You can get dynamic functional information as things move around. There's a variety of labels. And you can also do super resolution fluorescence to give you organelle level resolution. For electron microscopy, on the other hand, you can go right in at macromolecular or nanometer scale resolution, and you get information on the surrounding reference space. So you see what else is in there besides your targets. You see everything, and you see the labeling in a cellular and a tissue context. Correlative microscopy. Correlating light and electron microscopic data multiplies their information value by giving you localization, interactions, and structures at different levels of magnification, where you see complementary processes and complementary functions. To look at the characteristics of the probes, the techniques, and the methods in a little more detail, here's light microscopy, which is largely fluorescence in the case of FluoroNanogold probes. And you've got labeling options of dyes, fluorescent proteins, or quantum dots. You can do live cell imaging, the option of super resolution. You have the structural aspect of labeled molecules with respect to other cellular components, however, which can't be directly visualized when you're looking at fluorescence. It's an in-the-dark technique. You see your target, but you have to fluorescently label anything that you want to look at. For electron microscopy, on the other hand, you have a choice of methods. You can have TEM or SEM. You can have direct visualization of your targets of different electron density, or you can use high atomic number reporter molecules and probes and labels. Live cell imaging is much more difficult, but you do have very high spatial resolution, 4 to 8 nanometers, maybe higher for some high resolution techniques. A limited field of view, semi-quantitative labeling, and localization of molecules of interest in relation to the cellular context and to other structures. And you can obtain detailed three-dimensional information from 3D tomography. Now here's an example of fluorescence and electron microscopic techniques compared. Here's conventional fluorescence, super resolution fluorescence, and here's electron microscopy. And here's the overlay showing how these techniques compare and match up. And here's a higher magnification super resolution image compared with the electron microscopic image showing the individual gold nanoparticle labels. And here are the two images overlaid. And finally, an elemental analysis going along these lines in the different images, showing the signals from the different elements and the different components of this system as you travel across what in these cases are mitochondria from COS7 cells. Correlative challenges. It's not easy doing correlative microscopy, and there are a number of challenges to be overcome in getting good correlative results. Large differences in magnification and resolution have to be mapped and resolved. The region of interest can be entirely missed at the EM level, and you need a dual label for both modes of observation. The specimens themselves are very different. You may need much thinner sections for EM, and thin cryosections are very difficult to use for both LM and EM. There's fluorescence quenching by the gold, which we'll discuss more later. There's also background fluorescence, which needs a careful choice of fixatives and ancillary reagents. Sample preparation for tissues requires dissection and fixation, embedding and sectioning, then immunostaining with permeabilization. And you have to identify the region of interest by light microscopy, post-fix immunogold, dehydrate and embed, block, trim and section, and you can label at this step too. And finally, electron microscopy. And for cells, they must be grown or cultured directly on cover slips or slides, then fixed. Then immunostained with permeabilization. The region of interest has to be identified at the light microscope level and marked for EM. Then they need to be detached, embedded and sectioned, labeled by pre or post embedding, and finally, electron microscopy. And for cryosections, those must be collected on an EM grid, labeled, and then analyzed by microscopy. Labels and probes. There are a variety of labels and probes that have been developed for simultaneous labeling at the light and electron microscopic levels, and we're going to look at a few of those and compare them with our FluoroNanogold probes. To start with, you already have a way of doing correlative labeling with green fluorescent protein and its variants, and then targeting gold nanoparticles to the GFP protein using an antibody against GFP, or an antibody against something which is expressed or co-expressed with GFP. And here's an example: localization of actin comets at sites of ASEM degradation. And in this case, the cells are expressing beta-actin GFP, which was then labeled using a Nanogold anti-actin antibody. This shows the labeling and the distribution of the fluorescence and the Nanogold labeling in the regions of the actin comets and in the regions of matrix degradation. Now, another way of doing correlative fluorescent and EM labeling is to use fluorescence photooxidation. And here's an example of this using ReAsH, which is photooxidized, treated with osmium, and then developed with diaminobenzidine, or DAB, to give an electron microscope signal. And here's an example of this, showing the photooxidation followed by the EM. And DAB with osmium has a characteristic, rather diffuse, fuzzy look to it, which makes it a very identifiable type of signal. The alternative is to use ReAsH with Nanogold. And in this case, you get a very punctate labeling with the Nanogold labeled antibody, where the individual gold particles are either visualized directly or enlarged, in this case with a process called gold enhancement, which deposits more gold onto them. And you can compare the nature of the staining, which tends to be continuous or diffuse when you use photooxidation with DAB. But with Nanogold, it's punctate, and the individual targets are identified by individual gold nanoparticles. And here, in fact, is the detection of targets with Nanogold, showing the punctate, individual, single label nature of the staining. Another type of probe that's used for correlative microscopy is quantum dots, or semiconductor nanoparticles. These fluoresce, and since they're also made of relatively high atomic number elements, they do show up in the electron microscope too. They do have some drawbacks. They have contrast and signal-to-noise ratios that are less than gold nanoparticles. They're just not as dense. Blinking can be an issue for fluorescence microscopy. They require thick coatings, which often make them large and give them poor penetration into cells and tissues. And they're also incompatible with some fixatives and counterstains, such as osmication. Nevertheless, they do actually give you fluorescent and electron microscopic labeling, as is shown in the bottom row here. But compare that with the top row, which shows labeling with fluorescent probes on the left, and individual colloidal gold, in this case 10 nanometer colloidal gold nanoparticles, in the center and right. And you can see that the contrast and the resolution of the nanoparticle labeling is much better with the gold nanoparticles. Fluorescent and gold probes. And now we're getting down to the FluoroNanogold and its applications. And we're going to talk a little bit about colloidal gold versus FluoroNanogold, the applications of FluoroNanogold, and some tips and tricks to help customers and to get the best results using FluoroNanogold. Colloidal gold probes have been used to make combined fluorescent and gold probes by the adsorption of fluorescently labeled proteins to colloidal gold. But these do have problems. The fluorescently labeled protein can dissociate and compete with the colloidal gold conjugate. They have different binding properties. There's fluorescence quenching due to the relatively large, relatively highly absorbing gold nanoparticles. As an alternative, people have used mixtures of fluorescent-only and gold-only conjugates. But that's also problematic for correlative labeling because gold particles are large, the probes are often very different in size and binding properties. And binding differences can mean that the labeling is not truly correlative. Here's the problem with fluorescence quenching, which I referred to earlier. Gold nanoparticles are actually pretty good absorbers of fluorescence emissions by resonance energy transfer, and that diminishes the fluorescence. And here's the overlay of the fluorescence emission of fluorescein with the absorption of our 1.4 nanometer nanogold absorption. Nanogold doesn't have the highest absorption in the region where many fluorophores emit. So the overlap cross-section is not tremendously high with nanogold. It is, though, much higher with some other fluorophores. This is the effect of fluorophore separation on the degree of quenching. And what we're showing here is separation along the x-axis in nanometers, and the proportion of native fluorescence which is retained at that separation. And the Forster distance, which is defined as the distance with 50% retention of fluorescence, for nanogold and fluorescein is about 6.5 to 7 nanometers. That distance, the Forster distance, increases dramatically with particle size. With nanogold, it's 6.8 nanometers. With 3 nanometer gold, it's up to 13 nanometers. With 5 nanometer gold, it's 25 nanometers. And by the time you get to 15 nanometer gold, it's up to 45 nanometers. And that really means you just can't make a combined 5 or 15 nanometer gold and fluorescently labeled immunoprobe. So we use FluoroNanogold with the 1.4 nanometer nanogold label, which results in lower quenching and conserves fluorescence. Fluorescent gold labels are separately attached to IgG, FAB prime fragments, or streptavidin for maximum separation and brightest fluorescence. And all the components are covalently linked for site-specific attachment and long-term stability. This shows the reactions that are used to attach the nanogold gold nanoparticle to antibodies and proteins. And we either use monomalayamido nanogold to label thiols, or we use monosulfo NHS nanogold to label amine sites. So depending on whether your molecule has an accessible unique thiol or not, we'll use malayamido nanogold or monosulfo NHS nanogold to label it with the nanogold particle. And then after that, the fluorophore is usually attached to an amine elsewhere in the molecule. And that gives us the combined nanogold and fluorescently labeled FluoroNanogold probe. This is an example of staining using the first FluoroNanogold, the fluorescein and nanogold labeled FluoroNanogold probe. And this is the staining of SC35 pre-mRNA splicing factor in HeLa cells. On the top, with a primary anti-SC35 antibody followed by secondary fluorescein and nanogold labeled FluoroNanogold. In the bottom, a control without the primary. Here's the EM equivalent. And again, at the top, SC35 primary antibody and FluoroNanogold secondary, and in the bottom, omitting the primary. And as you can see, the staining pattern is very similar at both the light and the electron microscopic level. Here's an example of FluoroNanogold imaged by different modalities of microscopy. You can see fluorescence, DIC optics, phase contrast optics, and finally, at the bottom right, a higher magnification transmission electron micrograph after a couple of minutes of silver enhancement. Now, we moved on from fluorescein to use the much brighter, much more photostable, and much more pH-compatible ElixirFluor fluorophores. And this is ElixirFluor 488 FluoroNanogold, a bright staining of red blood cells. For variety, we've also expanded to add the ElixirFluor 594 FluoroNanogold for a red fluorescence. And here's the structure of the FAB prime and streptavidin ElixirFluor 594 FluoroNanogold conjugates. And here's an example of correlative fluorescent and nanogold labeling using ElixirFluor 594 streptavidin as a tertiary probe. This is labeling caveolin in ultra-thin cryosections of human placenta. And here you can see the one-to-one correspondence of the fluorescence and the electron microscopic signals. Another example, labeling proteins in Drosophila synapses and visualizing with fluorescence and with electron microscopy. Here's FluoroNanogold for SEM. And in this case, what we're looking at is the overlay of the secondary electron signal, which is the regular signal as white is used to visualize, in this case, a plant chromosome with a constriction. And the constriction has been labeled using in situ hybridization with a biotinylated probe detected with ElixirFluor 488 FluoroNanogold streptavidin, followed by gold enhancement. And the yellow signal is the backscatter signal from the gold, showing the gold nanoparticles labeling precisely over the constriction. Here's FluoroNanogold for correlative fluorescent and atmospheric SEM. And here's the results showing tubulin labeled with FluoroNanogold at the fluorescence level and in the atmospheric SEM. And then finally, at higher magnifications, showing the individual microtubules quite well resolved at 17,000 magnification. Here's fluorescence and X-ray fluorescence, showing optical fluorescence and X-ray fluorescence from the gold. And in this case, co-localization of gold-labeled Golgi apparatus with selected elemental maps. A word on super-resolution light microscopy. Although it has higher resolution than conventional fluorescence microscopy, it doesn't really replace electron microscopy as much as provide another set of complementary data. It doesn't quite achieve macromolecular resolution, although it does achieve organelle level resolution. It's still a dark field technique, and the images don't really provide a morphological context for the signal. The instruments are relatively expensive. There are competing modalities, and the development of probes for combined super-resolution optical and electron microscopy is challenging. The latest addition to our FluoroNanogold range is ElixirFluor 647 FluoroNanogold, which is actually intended for correlative super-resolution light and EM, especially with storm, for which the ElixirFluor 647 fluorophore is very well suited. And this is showing, again, the labeling of blood cells at the immunofluorescence level. FluoroNanogold is available as IgG conjugates. It's also available as Fab prime conjugates and streptavidin conjugates. So you have a choice of different sizes, different binding strengths. The IgG will bind more strongly because it has two antigen combining regions, and different penetrating abilities. Because being only 1/3 the size of a whole IgG, the FAB prime fragment will get in more quickly and diffuse more quickly into the center of thicker or larger specimens. So to sum up FluoroNanogold, you can check your labeling by fluorescence before you start processing your specimen for EM. So you know before you start whether your labeling has worked or not. It's intended and optimized for CLEM, correlative light and electron microscopy labeling. You can distinguish different targets at the light level using different fluorophores. You can distinguish targets at the EM level using differential silver or gold enhancement, which is applying one probe, developing with silver or gold enhancement, then applying a second probe, developing with further silver or gold enhancement to give you two different populations of gold nanoparticles enlarged to different sizes. To end, A few technical support tips and tricks for getting the best results with FluoroNanogold. First up, it's worth noting that optimum conditions for fluorescent and gold labeling may differ, particularly things like the concentration, incubation time, or dilution of the probes, and some compromise may be required to achieve the best results or the optimum combination of results from both modalities, and some trial and error may be necessary to find the conditions that give the best results. It's often worthwhile increasing the concentration of the FluoroNanogold conjugate 5-fold or 10-fold. Then when you know you can see the signal in both modalities, you can perhaps decrease the conjugation again to control the background, or decrease the concentration again to control the background. Longer incubation times are sometimes helpful. If you're using fluorescein FluoroNanogold, often the Alexa Fluor 488 will give much brighter, much better results. Eliminating background sometimes requires quite rigorous or stringent washes and conditions, as both fluorophores and gold labels can interact non-specifically with biological materials. We find the most effective blocking agent is 5% non-fat dried milk, which you should use for blocking and for incubation with FluoroNanogold conjugates. Set the camera exposure manually. Often automatic exposure gives you longer exposure times, and this produces higher apparent background. Sodium citrate buffer is very good for washing. Use 0.02 molar sodium citrate. pH 7.0 works with Nanoprobe's HQ silver enhancer. If you're using the Dancher formulation silver enhancer, pH 3.5 tends to work better. It's always a good idea to control or reduce hydrophobic interactions, and you can do that by washing with 0.6 molar triethylammonium bicarbonate, and here's the reference for that. Or you can add a small amount of detergent, 0.1 to 1%. Saponin is often a useful detergent for these applications because its effects are reversible and it can be washed out and allow membranes and other disrupted structures to reform afterwards. There are challenges to correlative microscopy. The media and specimen characteristics must be suitable for both modalities. It's a challenge also making sure that the labels remain visible by both techniques. You have to be able to see the label by EM under the same conditions in the same specimens as you're seeing the label by fluorescence microscopy. Both labels must work in the observation medium. The fluorophores must be compatible with the medium that's used for EM specimen preparation. And some people have found things that work and techniques that work for helping that. Hydrophilic resins tend to preserve fluorescence. And here's a couple of references by Luby, Phelps, and Keene for specific hydrophilic resins and specimen preparation methods that do help to retain the fluorescence at the EM level. Uranyl acetate preserves GFP fluorescence. Glutaraldehyde tends to kill fluorescence. So to avoid fluorescence loss, you have to avoid glutaraldehyde fixation. And Peddy et al. Found that uranyl acetate is actually a good alternative and preserves the fluorescence much better. Even for ultra-thin EM sections treated with uranyl acetate produce enough fluorescence for you to get both fluorescence and EM signals. And here's an example of that, showing the fluorescence labeling and the electron microscopic labeling. Fluorescence can be reactivated by certain chemical conditions. And typically it's reduced in specimens embedded for EM. So it's hard to observe fluorescence in EM under the same conditions. But LR white, glycol methacrylate, or methyl methacrylate embedded specimens that are treated with 0.1 molar sodium carbonate buffer at basic pH, 11.6 for 2 minutes, will restore the fluorescence. And the fluorescence from GFP variants, like EGFP or EYFP, can be restored to levels normally found in neutral buffered solution by this method and this approach. And again, here's the reference for that. And here's an example of showing chemical reactivation of fluorescence by this method. So in conclusion, FluoroNanogold is a dual-labeled immunoprobe with both a gold nanoparticle label and a fluorophore. You can use it to check your labeling by fluorescence before EM processing. So it's a way of doing verification and quality control and checking immuno-EM labeling before processing. FluoroNanogold is ideal for correlative light and electron microscopy and other correlative methods as well. It's available with a range of fluorophores, Alexa Fluor 488, 546, 594, and now Alexa Fluor 647 for super resolution fluorescence, and also with fluorescein. And it's available in IgG, FAB prime, and streptavidine conjugates for the widest choice of binding modalities and allowing you to select for the strongest binding, the highest specificity, or the fastest penetration. So thank you for listening to this presentation and watching this presentation. If you'd like more information, please visit our website. Here's the address of our main page for FluoroNanogold products at nanoprobes.com. Thank you again. And if you have any questions, please email us at tech@nanoprobes.com or nano.sales@nanoprobes.com. Thanks, and have a good day.